Thanks a lot, Erik. Thanks a lot, Tom. And thanks everybody for coming. So, welcome to this book launch event for my first book, which I've titled Foundations of Computer Science. So, a little bit about me first. I have a PhD in computer science from the University of Oslo back in 2013. I now work as the CEO of Deploy.no, which is a cloud service provider. There I do everything from assembling the machines, programming all the systems, and even a little bit of sales and business. I have been doing active research since about 2009. And now my research is mature enough to collect the first results in a book. So, usually in academia they have this slide with the research method, but this is a slide where most people don't really pay so much attention, because that is not something you think about a lot or pay a lot of attention to. But before I did my research work, I gave it a lot of attention. So, my first goal when I started my research was that I wanted to undertake a large-scale project. So not just a small project, which is very typical in academia. You have many people who work on many small projects, and then you have the risk of losing the big picture. Another thing I did was that I wanted to approach science with this mindset of knowledge is power. In academia, it's very typical to think of knowledge as something you should contemplate and think about, and you get pleasure out of it for that reason. But I view it much more that you acquire knowledge in order to increase your skills. So I'll come back to that point more. I wanted to check everything I knew and concluded thoroughly. This is also something less typical. And when I talk about this part of the method to people, they will say, isn't that a lot of work, for example? But the thing is, if you don't do that, then you risk building or trying to build on something that is wrong or a misunderstanding. So this is an important part of the method. And the founder of the scientific method, he called this the idols, that human beings have a tendency to fall into certain traps. And you have to be very careful not to fall into those traps. Another thing was to confidently attack the problems. Because you have this cultural trend of skepticism, where science is regarded as very hard, very challenging. And I wanted to look at reality firsthand. So I wanted to shun claims of authority, that somebody claims that something is true because somebody said so. Shun lazy dismissals. I've experienced this a little bit because people will, because of this point here, when many people work on many small projects, it's easy to think that this was just something they did in a week or two, and they probably did a mistake, so we just dismiss it. And then we have this point, factioning, disputation. Factioning is when you have competing factions that don't want to talk to each other. And they build up their own set of theories, and they don't cooperate. And disputation is where you pay a lot of attention to what others have said on the topic and try to disprove them. But I instead wanted to just focus on looking at reality and see what we find. Also heavy use of inductive logic. This means that whatever conclusions I come to, I've come to them because I've looked at reality. Looked at, for example, looked at many production systems instead of trying to take some theory and then deduce conclusions. An interesting point here is that in science, there's a lot of focus on deduction. So if you arrive at a conclusion that is different than others, then they will think, you probably did some mistake. So you can dismiss it. But when you work inductively, when you look at reality very carefully, then you're not in that big of a risk to fall into like a single error will break your entire conclusion. Because here, if you make an error, you can correct it by integrating this new instance as well. I think this quote is quite nice. This is a quote that captured how people viewed science in the scientific revolution. And Bacon had just, or 40 years ago, published his book on the scientific method. And you had this huge flurry of scientific advancements and new discoveries. And to celebrate the Royal Society, a poem wrote, a long poem, but I think this one is quite nice because it captures this feeling they got when you had all these advancements. So the poem says, ridiculous and senseless terrors make children and superstitious men afraid. The orchards open now and free. Bacon, the father of the scientific method, has broke that scarecrow deity. Come, enter all that will. Behold the ripened fruit. Come, gather now your fill. So the idea was the skepticism of the past had stopped people from actually trying to look into science. But when they released that limitation on themselves and just looked at it instead, then this is the feeling they got. Another very good quote from Bacon is that a lame man on the right road beats a runner who misses his way. So if you follow the right method, you don't necessarily have to be the fastest runner. The most important way is that you go in the right direction. Okay, so the way I view science is that you have, throughout history, what I call the main line. So this is where time goes on, and we accumulate more and more knowledge as we go along. But we have these branches going out here, and these represents where people make an erroneous conclusion, and then they build on those. And what happens is that they will follow that path for a little while, but then the people working on actually discovering the truth will cause these to seem obsolete. You might have heard this term floating around, paradigms. And this is the idea that there is no reality. There is only a group building up a view of something, and then they are in the right. And then another group builds up another theory, so they are right. But I view it instead that science is that to look at reality and try to discover more and more about what is true. And what we see in the world is that as we gain more and more knowledge of reality, we can produce more and more. So we get more and more wealth. So that's how it manifests itself that we're going forward. But in cultures that in a sense integrate something wrong, they lose their ability for production. You also have this quote here, which is also from Bacon. Truth is the daughter of time. That as time goes on, it becomes more and more, well, the truth builds up a good case for itself. So, when I worked on the book, I had a research program. What kind of challenges that I want to tackle or to advance. And the first problem is what I call the programming language problem. It can also be called the cooperation problem. And we see this out in the world. We see that programmers cannot work on different projects. Now, of course, a programmer can work on different projects if the projects use the same technologies, right? And we can train a developer to work on a new project if we give him a few months or a year. But it is definitely something we observe, that a programmer that works on a very different programming language cannot just be added to a project. We also see that programs cannot be shared or reused. Again, you can reuse programs within a programming language, but usually not cross-language. There are hundreds of programming languages, but the top 20 is used by 80%. There's fierce factioning between groups that advocate different programming languages. And there's even rudeness and bullying. It can get quite tense. But I think this problem is solvable. And the reason is that the fundamentals of how we program a computer has remained the same all the way from the beginning. As Eirik mentioned, Babbage invented the computer in about 1840. And then we had many of the building blocks we still use today. So the fundamentals of how the computer works has remained the same from Babbage, and then to the first computer built by Aiken, and then to the first real large-scale industrial computer system, and of course to the modern PC. The second problem is the code rot problem, or the legacy code problem. Programs are observed to stop working over time. Programmers become less interested in working on some code over time. And we hear this is a huge issue. We heard here the term outdated code, technical debt. And I like to think of it as fashion changes. Again, I think this is solvable because code is digital, so the code itself doesn't rot. And again, the fundamentals of how the computer works has remained the same. The bug problem, security problem. Programs do things we don't want them to. Program fails, and programs allow unwanted people inside. And here we have what Bacon calls an addition of skepticism. People actually claim that it is impossible to remove bugs from programs. A conclusion that has its root in academia and Alan Turing. But again, this isn't the case. Computers are deterministic and finite. The reason why Alan Turing thought you couldn't eliminate bugs was because he worked with an infinite computer. But an infinite computer doesn't make sense. The performance problem. We observe that programs are slow. Not all programs are slow, of course, but many programs are slow. And they often don't scale well with high load. Again, it is solvable. Computers are cheap. And if we run the math, they do have the capacity needed to handle a lot of challenges they meet. The whole code problem. It is difficult to look at the whole program. Usually when we work on a software system, large part of the programs we work on are opaque in the background, in libraries, in the operating system. Again, this problem is also solvable. All the code is somewhere, even in instruction form. The operating system problem. Programs for one operating system does not work on another. Again, there are many exceptions to this, but this is the general issue. New versions of operating systems come with breaking changes. They often contain bugs and security problems. They are very complex and difficult to understand, and again, they are opaque. The spaghetti code problem. So my view is that this was partially solved by structured programming, but we still observe today that as programs grow larger, they become more and more difficult to understand. And again, if we manage to build our systems hierarchically, then we know that we can keep the understandability high. The instruction set problem. We have many processor designs. Not entirely true is these three that are dominating these days. Programs that work on one don't work on the others. And again, we get this problem that new versions break all programs. The memory problem. Programs use a lot of memory. Memory leaks are common. And computers must be restarted regularly. I've actually seen companies that restart their systems every hour. So yeah, this is an issue. The second to last one here is the error handling problem. Many programs give silent or vague failures. For example, an error occurred or something went wrong. So yeah, you have to start to debug that situation somewhere else. And then finally, the testing problem. Many programs are difficult to test reliably. Tests are expensive to make, and tests also rot. They stop working on that. So, I think that's it. No, actually not. The software cost problem. So software development is costly, and software itself is costly. Yeah, okay. So these are problems that I'm interested in, and that I wanted to have as a base for doing my research. Whether I would make any advancements on them, of course I didn't know. But the reason why I wanted to have a research program is that I wanted to make clear which challenges I wanted to attack. And this then goes into the style of the book. Because I think if you are interested in these problems, then I think you will find the book interesting. I present solutions or advancements to these problems in a straight way. The book does not contain a lot of disputations, related work, or references. And the reason for this is that I wanted to have a book that captures a point on this line you saw earlier. I wanted to capture a point on this line where this is what we know very well at this point, and then hopefully advance it a bit. And to anyone who reads my book and disagrees with my solution, I'll be more than happy to look at an alternative, of course. But I don't think it should be 10,000 pages, because knowledge in computer science should be more accessible than 10,000 pages. So. Okay, so some analogies to the solutions I present in the book. Music notation was invented around the year 1000, and it has remained the same since. And the reason why it has done so is that this guy, when he worked on it, he hit the fundamentals, what really is music and how do we capture it. So we can still read and play music from the 1500s, But who here would pick up code from the 80s and try to compile and run it? It probably, yeah, it might work, but another analogy is the Latin alphabet. It consists of a few letters, as opposed to traditional Chinese, which has 8,105 letters you have to memorize. And here we have some text from the Roman Empire, which we can still read the letters. Of course, we can't understand it unless we know ancient Latin. That's a different problem. But one thing I should note here, that space was not enough. So that's something they will add to the Mainline of later. And then there's created complexities. A lot of what's going on in when we build computer programs today, I think, is created complexity. And what I mean by this little drawing here is that when we build programs on top here, it looks very complicated and it's very difficult to solve certain issues. But if we understood what was hiding beneath there, maybe it would be easier to solve the problems. Okay, so let me introduce a few of the results that I present in the book. So, in the beginning of the book, I talk about that the purpose of computer science is to discover knowledge for producing with computers. And I think this clears away many issues that you primarily encounter in academic computer science, not so much in industry. And this is the source of the infamous industry-academia split. And it's very unfortunate because many associate science with contemplation of religious-like ideas. And this is something you see a lot of in academia, so I don't blame people for having that impression, but I don't think it's the right impression to have of science. And actually, I think many are skeptical to the book because they assume that what I will do in the book is to contemplate complex ideas that have no use in the real world. And of course, I could have chosen a different title to avoid that, but I think the classic view that science is something we do to produce or to build our skill is something that is worth preserving. Another point is that valid programs are those that solve production problems. So when we build theories about how we should build programs, we shouldn't base our reasoning on programs that solve made-up problems. Again, if you are from industry, you will think that this sounds weird, but it's a huge problem in academia. A big idea in the book is what I call the computation infrastructure distinction. This idea runs throughout the book, so much that part 2 of the book, or the book is split into 2 parts basically, and one part deals only with what I call infrastructural computer science, and the other one with computational. If you pick up any random book on this topic, then you will basically only be introduced to this part. And the reason goes back to academia, and again Alan Turing, because he argued that only computations exists. So he didn't integrate into his theory, for example, what to do with a screen, a disk or a keyboard, or many other things you connect to a computer. Okay, so computational computer science deals with what you can do with only a CPU and memory, while infrastructural computer science deals with what you do when you connect many devices together. So for example, connecting many CPUs together can form a large distributed system. And if you connect a series of CPUs together with a disk, for example, you can create a redundant disk system and many, many other things. So this is captured in this part of the book, which is traditionally not covered in a book like this. And it's one of the reasons why it feels so, many of the books on this topic feel so uninteresting, because this part is very well understood, but this part hasn't gotten that much treatment. So in the part where I talk about infrastructural computer science, I talk about devices. And the 5 main devices I talk about is the disk device, where you persist information, the screen, where you draw images, the clock, where you get the time. These 3 are well known, but these 3 I've created the term for myself. A processing unit is basically a CPU and RAM. It doesn't have to be the CPU, it can be a CPU running on a network card or a graphics card. So it's a much wider concept that captures much more than just the CPU. It captures anywhere where you have processing and RAM. And then this one, processing unit controller. This is the device that controls which processor is running and which program it is running. I then move on to talk about 4 ways you can combine the devices with each other. 4 ways you can combine the devices. So in part 2, I talk about these things, and then I present the results in this table here. And here we can, for example, see what happens if we combine disks. Then we get what is called RAID. But if we split the disks, then we got what is called a partitioner. If we share the disk, then we get a file system or a database. And if we do what is called decoration, then we can make a cache, disk cache or a disk scheduler. Now this is going in this direction. If you look at this direction here, we can see that if we try to share these devices, then we get the file system, we get the windowing systems, and actually an entire operating system is named after just this one here, where how we can share the screen, and we can share it using Windows. And we have a CPU scheduler and a prioritizer. So what we can see is that the sharing of resources is in this column here, while the static allocation of resources is in this column here. So here we find the hypervisor, and here we find the operating system. So this way of looking at the devices and how we combine them is very useful in order to understand what's going on with these different kind of things. Now, an interesting thing to mention here is that a lot of stability problems that we see in the wild is because people chose a sharer instead of a splitter. So, for example, if many people come to a website, it's a huge problem that it falls down. And this is because they didn't understand the difference between a sharer and a splitter well enough when they did the architecture of the system. Yeah. For each of these devices, I present an instruction set. Instructions are the basic thing a CPU can do. So a CPU does one instruction after the other. And I present an instruction set for all the devices I talk about. And as far as I know, this has never been done before. And this is usually hidden away in many different ways. But here I created an instruction set with just a few instructions that captures everything these devices can do. And this is for infrastructural computer science. In computational computer science, the instructions are very well known. We have the usual instruction set that you get for computers today. But I present an instruction set of 194 instructions that I think are more timeless. This goes back to. And an implementation of these instructions is about 1,600 instructions on a modern CPU. So this here is an attempt at a solution at what I call the instruction set problem that I talked about earlier. And it also tries to tackle part of the programming language problem in that here you have a very short list of instructions that captures most of what these devices can do. I then present a programming language, but I only present a programming language for the computational part. And the reason for this is that what I'm doing right now is to work on a programming language for the infrastructural part. But that is something that nobody has ever done, or they are starting to advance on this, but there are very few results on this. So therefore, I have a programming language for the computational part and then use the instructions for the infrastructural parts. An interesting result is that the development and testing of infrastructural programs, that means programs that interact with the disk screen and other processing, other CPUs, distributed systems, can be done using only the computational programming language. And this means that you can develop a program, develop and test a program in a 100% deterministic setting. And then when you run it in production, you replace the deterministic parts with an actual disk or an actual inter-process communication system. And this is quite well known in the development community as test-driven development. But this takes it one step further, where you can actually do test-driven development reliably on not only computational code, but also code that involves, for example, a clock or another CPU. And based on this, you get the impression, or I try to convey the impression, that it is possible to program the computer in a more timeless way. Not that we code Python or code Java, but we code the computer. So a few years ago now, I built this programming language and commercialized it as a technology called ProgSpace. And I started building a lot of libraries. And this collection of libraries have now expanded to a lot of libraries. Some of these libraries have locks on them, and that is because this is something I have recently developed and will release, possibly under a new brand name. But the point of this is to build a large library of code in a timeless language. So if you click in on any of these libraries here, you get the option of downloading it in any programming language. For example, you can download it in C or in Java C#, etc. And you can actually, the functions here, you can just run in the browser as well, because I just download the code in JavaScript, of course, and then run it in the browser. And now that I'm working on what I call infrastructural computer science, where I interact with devices, that kind of code can also be added to the library. One interesting thing here is that many of these libraries have now been running in production for 3 or 4 years. Yeah, and I will come back to why that's interesting. Memory handling. One result in the book is that programs have 2 main forms. And as you can see, these 2 terms come back again. One for computational code and one for infrastructural code. And you can actually use something called region-based memory to manage memory in each of these situations. And one way I think of a region-based memory is that it is as convenient as garbage collection, but as lean as manual memory management. Error handling. I again talk about how we deal with the error handling in the computational case and in the infrastructural case. Yeah, I'll only briefly mention this one. In the computational part of the book, I talk about how to deal with numbers, which is a big issue in computers. And I detail a process for how I think you can build what I call timeless programs. And that means programs that you can use in any programming language. Well, not all, but there are a few exceptions. But and that can be reused, as I used to say, across space and across time. So if you go back to this line here, if this line here represents now, what I try to do, I might not have achieved that, but what I try to do is to fix a point here on this main line. So it might in a little bit into the future. So it might be the case that there are many interesting trends being developed now that prove to be a part of the main line. But this is at least what I attempted to do in the book. So I try to capture the existing good knowledge, and I try to build a little bit more on my own. That's the purpose of this slide. So the future, what will I do in the future with this project? I'm not known, I have no reputation, and of course there are no expectations that this book will be interesting. And I think that one reason about that is the mistakes about science that is for contemplation, for example. But I think I have a very interesting thing I can leverage. I have a large collection of computational and infrastructural libraries that is growing every month, and that is being battle tested in production systems all the time. And the interesting thing here is that the code actually gets better with time and not worse. So one thing I will plan to do is to, when I am confident enough about some of these libraries, I will start issuing rewards for finding bugs in them. And of course, if people come back with bugs, I'll fix the bugs. But if there aren't any bugs that have been discovered for a little while, I will increase the rewards. So just look briefly back at this collection here. So I'll add another row here to this overview, saying the current reward of finding bugs in these libraries. And my hope is that this will motivate developers to have a look at the code, maybe read the book, and learn more about what this is. Because there are many programming languages out there, and many people claim that they have good and interesting solutions. But if I can actually put up like $100, $10,000 there, then I think I will trigger some interest. And hopefully, when many of these libraries are have been inspected by many people, have been battle tested in production, and no bugs has been found for, let's say, 3 years, then I hope that we have code that can be reused across the world and indefinitely into the future. So I plan to grow the library with more code. I plan to create a computer science research lab. If anybody wants to join me in doing computer science research, you're welcome. We will do hiring in our cloud service company, where we build software based on these ideas. So if you know anyone who wants to work with cloud services, let me know. If you have questions, would like clarifications, or have better solutions than I present, then let me know. Yeah, thank you.